Chapter 5 Homework, questions 8, 9, and 11. List the 3 requirements for repeated trials of an experiment to constitute Bernoulli trials. So if you want to do, for Bernoulli trials, each trial should have 2 possible outcomes. One is success and the other one is we call failure. So only 2 possible outcomes. And each trial should be independent, and the probability of success should be the same for each trial. And here's an example in here. When you toss a coin, theoretically the probability of getting heads is going to be 1/2, and it's the same for each time you toss a coin. It doesn't change. So we have that requirement. And it has 2 outcomes, which is heads or tails. 2 outcomes, and also each when you toss a coin, each event is independent. So the tossing a coin is an example of a Bernoulli trial. What is the relationship between Bernoulli trials and the binomial distribution? So when you get the Bernoulli trials, when you get your results, basically binomial distribution just takes your results and it lists or it actually distributes the success of the outcomes for the Bernoulli trials. And here's an example. Let's say that you work on this. Let's find the Bernoulli trials and the binomial distribution for this information. So they found that a person who's 20 years old have a chance about 80% to be alive when that person is 65. So we will use this information, and we will try to find the Bernoulli trials and the binomial distribution for 3 people who are 20. If there's 3 people who are 20 when they are 65, what are the outcomes who's going to be alive? So all 3 can be alive. The first 2 can be alive, the third can be dead. Or first can be alive, second can be dead, or the third one can be alive. So actually these are all the possible outcomes for these. And if it's 80% chance to be alive, which is the success part, when you convert 80% chance can be converted to probability like 0.8. So if the probability of being alive at age 65, if it's 0.8, probability of the failure, which is being dead, is going to be 1 minus probability of being alive. That's going to be 0.2. So we found these probabilities. Now let's find the probabilities for the Bernoulli trials. If all 3 are alive, if all 3 is the success, because they are all independent events, you multiply the probabilities and you get this number in here. And then you do the same for the rest. You find all the probabilities. So this part is the Bernoulli part. Now, how do we distribute this? By using binomial distribution. So this part is going to be the binomial distribution. So binomial distribution gets the success part and there's distributes in here. So let's say that X is the number of alive people. So when X is 0, it means that nobody is alive. It's all failure actually. And that one is only the all 3 failure part. And this is the probability. We put the probability in here. If 1 person is alive, it means that there's 1 success and 2 failures, which is that one. 2 failure, 1 success. 2 failure, 1 success. 2 failure, 1 success. And they have the same probabilities. Because there's 3 of them, you add the probabilities to find the probability of having 1 person alive and 2 person dead. if 2 people are alive, it means that there is 2 success and 1 failure. So when you look at in here, 2 success, 1 failure, 2 success, 1 failure, 2 success, and 1 failure. You do the same thing, you add the probabilities, and you'll find the probability of being alive for 2 people. If number of people that are alive is 3, it means that all 3 are alive, which is all 3 is success. That one, this one, the top one, and this is the probability for all 3 success. This is how we distribute. This is the binomial distribution of the Bernoulli trials. Question 11. Explain how the special formulas for the mean and standard deviation of a binomial or Poisson random variable are derived. So basically, the only thing we do is we just substitute the probability formula in the mean and standard deviation formula, and then we use math and simplify. For example, how do we derive the mean for a binomial variable? For a binomial variable, this is the formula to find the mean, and in here, as you see, we see the probability we see the probability in here, and this is the formula for probability. We basically take this expression and plug in here. When you plug this in here, that's what you get. And we all know that this is binomial coefficient, and we can write this expression by using factorial notation like that. So after we do that, we start simplifying. We do all these math and we find this. So basically, let me quickly explain how we do simplification. So we have listed that it says x from 0 to n. If x is 0, the whole thing is going to be 0, so it doesn't add anything, to our sum. And we can just exclude x equals 0, and we can start from 1. And when we start from 1, in here we have x in the numerator and x factorial in the denominator. And I know that x factorial can be written as x times x minus 1 factorial. So in here, x and x times x1 minus x minus 1 factorial, the x's cancel out, and we only have x minus 1 factorial in the denominator. And after we get this, because the n in here and the p in here, they do nothing with x, so I can just take them out in here. When I take n out, I have n minus 1 factorial left, and when I take the p out, I have p to the power of x minus 1 x minus 1. And after I do that, because I have n minus 1 and x minus 1, I just define new variables. For n minus 1 I say m, and n minus 1 I say m, and x minus 1 I say y. I define new variables for these expressions. And then I also change this, the upper limit and the start, the number that I start, and I get this. And I know that this expression in here actually is the binomial coefficient. And when I look over here, this part, this is actually binomial theorem. And that part tells me that this is the mth power of p plus 1 minus p. P plus 1 minus p equals 1, because p and minus p cancels out. And that expression equals 1 to the power of m, and that's going to be 1. The only thing I have left in here is going to be n times p, so the mean equals m times p. For standard deviation, I do exactly the same thing. This is what I will find at the end. This is the probability formula, and I will plug this in here. And in this math part, I only could find the variance, how to calculate the variance, but it doesn't matter, because standard deviation is square root of the variance. So after I find the variance, square root of the variance is going to be the standard deviation. So let's see what I'm going to do in here. I will take this part only because I know that mu equals n times p. I found this earlier. And mu squared is going to be n times p squared. I will work on this part. So when I take this part in here, I plug this in the formula and that's what I get. And there's x squared. I'll just change this x squared to x times x minus 1. And that also is gonna cause me to lose one of the NP part because I subtract it. But I'm going to add it at the end. It's okay. So in here, when I plug in 0 for x, the whole thing is going to be 0. When I plug in 1 for x, the whole thing is going to be 1. So I will not start from 0. I can just start from 2, like that in here. But I also know that I can simplify. I can cancel x times x minus 1 because there's x factor in the denominator. So they cancel out with the x times x minus 1 of this expression, and I only have x minus 2 factorial here left. So I get this expression. After I get this expression, what I do is I just take out n, because it has nothing to do with x. I take it out. And I take out, I take out n times n minus 1. I take this out. And I also take out p squared from here. So this is what I get, what I take out. And the expressions that are left in here, I will just rewrite n minus x in a different form. I will write n minus 2 minus x minus 2. It's going to be the same expression, and I will put that in here as well. For n minus x, I will put n minus 2 minus x minus 2. And then I will define new variables for n minus 2 and x minus 2. So after I define new variables, in here I will get this expression. And again, it's the same theorem, the binomial theorem. That's gonna, this part is gonna be 1 again, because this part equals p plus 1 minus p to the power of m. It's the same expression, it's gonna be 1. And I only have in here n times n minus 1 times p squared times 1, which equals actually n times n minus 1 times p squared. So remember in here, because I excluded one in here, which is NP, now I add NP in here. And let's go back here. So this expression in here equals n times n minus 1 times p squared plus n. That's what it equals. And also I subtract mu squared, which is np squared. Now I also add that one. And I take out NP. I factor out NP. That's what I get at the end. And that's the link for the video for this explanation. So how do I derive the mean and standard deviation for a Poisson random variable? I do exactly the same thing. This is the formula for mean. This is the formula for the standard deviation. And for Poisson random variable, that's how we this is the probability formula, and I just plug this in here, and then after I do all the math, all the simplification, I find that mu is lambda and sigma is the standard deviation is square root of lambda. And this is the link for the video of the explanation. I could not have time to record the explanation in here. That's it.